just trying to share the screen. Okay. I think we will begin then. So today is the week 6 of the live interactive session. So last class we have been talking about, we started the session atmospheric thermodynamics, and we were talking about lapse rate, first law of thermodynamics, and all those things. So today we will continue that atmospheric thermodynamic portion as well. We will start. So today we will start with what is known as the potential temperature. So you guys remember that last class we were talking about virtual temperature. That we introduced the temperature, virtual temperature, which is basically the temperature that a dry air would have, which had the same density of a moisture parcel. So it was introduced to maintain the specific gas constant as that of dry air itself, instead of changing so as we discussed in the last class, there are two gas constants basically. One is specific gas constant for dry air, which is having a value of 287, and another one was specific gas constant for moisture, which was having a 61 or 461. So these things came when we are considering the such gas specific gas constant for 1 kilogram of a particular gas. So it basically depends on the gas, what the gas is. Is it water vapor? Is it dry air? So it basically depends on the type of gas that. So the issue with using the specific gas constant for moisture was that it basically depends on the amount of water vapor present in the air parcel that we are considering. So we'll have to keep on changing the value of Rm as the water vapor content in the air change. That's why we introduced a temperature known as a virtual temperature to retain R as Rd itself. Like we will in the equation of state P is equal to rho RT. We wanted to retain R as RT, so we introduced the virtual temperature. So when we are considering moisture air parcel, we can use the same equation of state. P is equal to rho RT into TB. That is with T will be replaced with TB. So we learned about virtual temperature in the last class. Temperature, which is basically known as the potential temperature. So potential temperature, which is basically represented by theta of an air parcel, is defined as the temperature that the air parcel would have if it were expanded or compressed adiabatically from its existing pressure and temperature to a standard pressure P0. So consider that as an air parcel in the atmosphere. So the air parcel is present at some other present at, let it be height, let it be 1 kilometer, 2 kilometer, 3 kilometer, something. So based on the height at which it is present, also changes, like the pressure decreases as we go up. So based on the height at which the air parcel is present, so what we do is that we bring the air parcel down to the sea level and measure its temperature. So that temperature is basically known as the potential temperature. So we bring the air parcel down by adiabatically compressing or expanding it from the existing pressure. So as the air parcel is bring down along the atmosphere, basically it will undergo a compression, because as we go up in the atmosphere, the pressure is decreasing. So the air parcel expands when we are going up in the atmosphere. So if we are bringing an air parcel from a higher level to lower level, it will undergo adiabatic compression because the pressure is increasing as we are coming down. So we are bringing an air parcel which is present at some level in the atmosphere to the sea level, which is generally taken as 1000 hectopascal. While bringing this parcel by adiabatically expanding or compressing it, the temperature that we are getting is potential temperature. So initially the temperature of the parcel was T. So consider that initially the pressure was P and the temperature was T of an air parcel. So let this be high. Oh, okay. Sorry. Sorry about that. You guys did. Okay, sorry. Okay. So I was talking about potential temperature. So potential temperature of an air parcel is defined as the temperature parcel would have if it was adiabatically expanded or compressed to the pressure level 1000 hectopascal. Okay. So consider that there is an air parcel which is at height, this height, which is having, suppose an air parcel is present at this level. So this is height, having a pressure P and temperature T. Now we are bringing this air parcel down to the level 1000 hectopascal. Then as we are bringing down, the air parcel will compress because this is at a higher height where the pressure is comparatively less. And when we are that the air parcel experience is basically increasing. So as we are bringing it down to 1000 hectopascal, there will be a change in temperature that will be occurring to the parcel. So temperature is basically known as the potential temperature. So in order to the temperatures of air parcels which are present at different levels, we compare the potential. So suppose one air parcel is present here and another air parcel is present at some different height. So we cannot compare the temperature of these parcels as such, like just like this, because these two air parcels present at different levels. So the properties or pressure that are experiencing is different. So we cannot just compare the actual temperature of these parcels. So what we do is that to make a comparison between these two air parcels, we bring both parcels down to a reference level, which is generally taken as 1000 hectopascal level. And then we find what is the potential temperature of these parcels. And then we compare the potential temperature of the parcels instead of comparing the actual temperature. So that's why potential temperature is basically used. So this is basically a conserved quantity for an air parcel that moves around in the atmosphere at adiabatic condition. So if we are considering adiabatic condition, or if we are considering last about talking about how the basic assumptions that we are making for an air parcel. So uh, generally the atmospheric motions are considered to be adiabatic. So generally for all the atmospheric motions, the potential temperature will be a conserved quantity. Conserved quantity in the sense that potential temperature will not be changing. When the parcel is undergoing an uplift or it is having a subsidence, the potential temperature of the parcel will remain constant because the motions are considered to be adiabatic. So yeah, that's about potential temperature. So the derivation I think is already taken in the NPTEL class, so I don't want to repeat the same thing. So this is basically the equation for potential temperature. I hope the concept is clear. So basically potential temperature is the temperature that an air parcel would have if it is adiabatically expanded or compressed to a standard pressure P0. So when we are bringing an air parcel down, it will undergo an adiabatic compression. Suppose we are bringing an air parcel which is at a lower level and we are taking it up. So it is having a pressure which is greater than 1000 hectopascal. Then we will have to take the air parcel up to 1000 hectopascal. So in that case, when we are taking it up in the atmosphere, in that case it will be undergoing an adiabatic expansion. So based on the pressure level at which the parcel is present, by undergoing adiabatic expansion or adiabatic compression, we are taking an air parcel from its existing pressure and temperature to a standard pressure P0. So while bringing it down or bringing it up, the temperature that it will attain is basically known as the potential temperature. So T is the temperature at which the air parcel was existing initially, and P0 is the reference level 1000 hectopascal as I told, and P is the initial pressure that the parcel was having. R we know is the gas constant, which is 287, and Cp is the specific gas constant at specific heat at constant pressure. So this is potential temperature. So just for acid revision, I will check what was derived. So if you guys remember, we talked about the different forms of first law of thermodynamics. So the basic form of first law of thermodynamics was dq is equal to du plus dw. Then if we are expressing it in terms of specific heat at constant pressure, it was dq is equal to cp dp minus alpha dp. Now as I said, atmospheric motions are considered to be adiabatic. So dq will be 0. In that case, cp dt can be written as alpha into dp. And according to ideal gas equation, P alpha is equal to RT, where alpha is the specific volume. Then alpha can be written as RT by P. Substituting it here, Cp into dT is equal to RT by P into D. Now by rearranging, we can write Cp by R into dT by T is equal to R dP by P, right? Cp by R into dP by T is equal to dP by P. Now we are integrating from theta to T. Theta is the potential temperature. Integral P0 to T dP by P. So theta is the temperature corresponding to the reference level P0, and T is the initial temperature and pressure. T and P is the initial temperature and pressure. So Cp by R into log integral of dt by T is log T by theta is equal to log T by P0. Log T by theta is equal to R by Cp log T by P0. We want to find T. T will become theta into P0 by T R by Cp. This is how the potential temperature equation was derived starting from the first law statement of first law of thermodynamics in terms of the specific heat at constant pressure Cp dt minus alpha dP, and we are considering adiabatic conditions. All atmospheric motions are considered to be happening under adiabatic conditions. So adiabatic in the sense no heat is added or removed from the system. So dq, change in heat, will be 0. So Cp dt will become alpha dP from the ideal gas equation, which is P alpha is equal to RT. Alpha is substituted, which is RT by P. So after substituting and integrating from theta to T in terms of pressure and P0 to theta to T in terms of temperature and P0 to P in terms of pressure, finally we will get the equation T is equal to theta P0 by P R by Cp. So this is the equation for potential temperature. So potential temperature is the temperature that an air parcel would attain if it is adiabatically expanded or compressed to the standard pressure level, which is 1000 MPa, to a standard pressure level, which is basically considered as 1000 MPa or 1000 hectopascal. So So now let's try to calculate the potential temperature of an air parcel at height 100 meter with temperature 5 degrees Celsius. So we know the equation for potential temperature. Theta is T into P0 by P into R by C. Theta we want to calculate. What all things are given? We have given the height Z, which is 100 meter. So this is the level at which the air parcel is present initially. So this is Z. This is the surface. Z is equal to 0. The air parcel is present at a height Z is equal to 100 meters. So the temperature of the pressure was 5 degrees Celsius at this height. Now we are going to bring down this parcel to the height Z is equal to 0 to the surface. We will find what will be the temperature at that level. So Z is equal to 100 meter and surface pressure is 1000 MV or 1000 hectopascal. 1000 millibar and 1000 hectopascal are same units. So basically the SI unit of pressure is Pascal. So into 10 raised to 2 Pascal it will be 1000 into 10 raised to 2 Pascal. So that is the value of P0. 1000 hectopascal. So first we want to find the pressure. What is the pressure at this level? At Z is equal to 100 meter. What is the pressure? That's what we want to find initially. So the equation that we have been using so far is P is equal to, considering an isothermal atmosphere, P is equal to P0 e raised to minus Z by H. So H, which is the scale height of the atmosphere, is given as RT by G. So the value of R is 2. Temperature is 5 degrees Celsius, which is 5 plus 273, which is 278 Kelvin by 9 point. Can you tell me what is the value of scale height? Is it clear? So we want to find the potential temperature, which is given as theta is equal to P0 by P by Cp. So we know the value of theta, which is given as we have to calculate the value of theta. We know the value of Z, which is given as 100 meter. We know the value of P0, which is 1000 MV or 1000 hectopascal. So now we want to find P. We don't know what is the value of P. So in order to find the value of P, we use the equation 0 e raised to P0 e raised to minus Z by H. We know what is Z. We know what is P0. We have to calculate H, scale height of the atmosphere. So H is given as RT by G, which is basically 287 into 278 by 9.8. Can you tell me what will be the scale height of the atmosphere? 8,140 kind of. So basically it is in meter. 8,000 meter or 8 kilometer we can consider. That is the 8,000 meter. For simplicity understanding, taking it as 8,000 meter. So H is 8,000 meter. And then, so we know P. Now we have to calculate theta. So theta is given as, the P is basically 278 into P0 is 1000 by P we calculated, P we didn't calculate, right? We just calculated H. Now we have to calculate P. P is 1000 into e raised to minus 100 by 8000. How much it will be? What will be the value of P? This. Can you tell me the value of T? So we found the value of H, the scale height, is 8,140 meter. It took us approximately 8,000 meter. Then the value of T is given as T0 e raised to minus Z by H. T0 is 1000. Substituting the value of Z and H, it will be 1000 into e raised to minus 100 by 8000. So what will be the value of T? Yeah, 987 hectopascal it will be. So this is the value of T. Now we have T0 we know, T we know, R is 287, Cp is basically 1004. Specific heat at constant pressure, that is a constant value. In case of air it is 1004. So what will be the final value? 278 into 1000 by 987, the whole raised to 287 by 1004. Yeah, it is coming around 278, 279. Yeah, 279 Kelvin. The answer was 279 Kelvin. So initially the temperature was 5 degrees Celsius or 278 Kelvin. We bring down the parcel to the pressure level 1000 hectopascal, and then the temperature became 279. Yeah. Temperature is also increased. Okay. So that is the potential temperature of the air. Okay. Okay. This is a question regarding the mixing ratio. So let's just revise what is mixing ratio that you have studied in the NPTEL class. So basically, when we talk about the moisture content in the air, there are different parameters that we use to define how much amount of water vapor is present in an air parcel. And what is the percentage of moisture that is available in an air parcel. So we generally use different parameters to define the amount of water vapor present in a parcel. So some quantities, some parameters like that. The first one is mixing ratio, which is basically first one is mixing ratio. It is represented by W, small w, and it is basically the mass of water vapor present in the air divided by the mass of dry air. Suppose if there is a parcel which is having a total mass of m and it has mv, the total mass is basically the mass of water vapor plus the mass of dry air. So the ratio between mass of water vapor present in the atmosphere by the mass of dry air is basically known as the mixing ratio, which is represented by W. So this is both are mass, so it is generally expressed in gram per kilogram. Because the amount of vapor present will be very much less compared to the dry air that is present in a parcel. So generally we say this much gram of vapor is present in this much kilogram of dry air. That's how we generally represent mixing ratio. And the value of mixing ratio is very high in tropics because the temperature is high. Rate of evaporation also will be high in the tropics. Tropics means that belt near the equator. So near the equator, that region is basically known as the tropics. So this is 0 degree. This is 0 degree latitude. This region, the region near the equator is known as the tropics. So we are basically The India and all are basically in the tropical region. From tropic 23.5 degree north to 23.5 degree south. Tropic of Cancer to Tropic of Capricorn. That belt is basically known as the tropics. So those regions where sun's rays are the maximum. So we have high rate of evaporation, and basically the mixing ratio, amount of water vapor content in the atmosphere will also be high in the tropics. Whereas when we go further up to the mid latitudes and then further up towards the poles, then the amount of the value of mixing ratio reduces. It is high in tropics and it reduces as we go up in the latitude towards the pole. So that's how it changes. So it is having a high value in the tropics. Now another quantity is known as specific humidity, which is represented by small q. So this is basically the mass of water vapor present to the total mass of air. So this one we were with respect to dry air we were discussing, and then this in case of specific humidity with respect to total mass of air it is represented. So mass of vapor to total mass of air is specific humidity. This is also expressed in grams per kilogram, since both are masses. So this, if we divide the numerator and denominator by mv, so it will become mv by md by mv by md plus mv by. So we are dividing the whole numerator and denominator by mv. So mv by md is basically the mixing ratio W plus 1 plus W. So the specific humidity Q can also be represented in terms of mixing ratio. This Q is equal to 1 plus W. So these are two important moisture parameters that we use to represent the amount of water vapor that is present in a parcel of air. So first one is mixing ratio, which is represented as the mass of water vapor present to the mass of dry air, which has a value of generally 20 gram per kilogram in the tropics. The next one is specific humidity, which is the mass of water vapor present to the total mass of air, mv by mv plus md. That is also expressed in gram per kilogram. And in terms of this mixing ratio, if we want to express specific humidity, we will get the equation is basically Q is equal to W by 1 plus W, where W is the mixing ratio of the gas. So that is mixing ratio. So now coming back to the question, suppose air contains water vapor with a mixing ratio of 5.5 gram per kilogram. So mixing ratio is W 5.5 gram per kilogram. And the total pressure, which is P, total pressure means the pressure exerted by water vapor plus the pressure exerted by dry air. So the total pressure is 1026.8 hectopascal. Calculate the vapor pressure P. So we know what is the total pressure. We want to calculate the pressure exerted by water vapor. So how much will be the pressure exerted by vapor pressure? That's what we want to find. So how can we find it? Okay. Generally, so this is the vapor pressure, but basically the partial pressure exerted by water. That is E. The partial pressure exerted by one of the components is basically E is equal of that particular gas by the total number of moles of the gas, like total of the mixture of gas that we are considering into P. So we are considering a air parcel, moist air having, which is having some moles of vapor and some moles of dry air. So NV by water vapor present by the total number of moles into the total pressure will give you the vapor pressure. So it is basically proportional to the number of moles of the constituent in the mixture. In the mixture that we are considering, how much it is present, how much vapor is present. It is basically proportional to that. So E can be written as number of moles of vapor to the total number of moles of the mixture. So NV plus NV into the total pressure P. Number of moles is basically given as mass, how much water vapor is present, the molar volume of water vapor by same thing. ND will be mass of dry air present to the total mass of dry air. The number of moles can be represented in mass in gram and molecular weight like this. So now into P. Right. So this can be, so if we are dividing it by both numerator and denominator. So here also we are multiplying a quantity 1 by md, and here also we are multiplying the quantity 1 by m. Then mv by md will become w by m by here, so w by md plus here md and md will cancel. It will become 1 by md. W by mv. Yeah. Now if we take mv outside, it will become w by w plus, here we will have to multiply mv by, this will basically become by w plus mv by md. This is molecular weight of vapor by the molecular weight of dry air. If you guys remember, the molecular weight of vapor is around 18.016 kilogram. Molecular weight of dry air was found. We found these values in the last class, not kilogram, gram, 28.9 gram. So this value will be 18.016 divided by 28.9 will give you a value of 0.622. This is basically equal to the ratio specific gas constant of dry air, the specific gas constant of moisture, RD by R. This is also having this value 0.622. So this value RD by Rn or MV by MD is basically represented as epsilon. So this is epsilon. So here we can write W by W plus into P. Now we have the vapor pressure in terms of mixing ratio. Now we can easily calculate the vapor pressure in this parcel of air. So what was the question? So suppose air contains water vapor plus a mixing ratio of 5.5 gram per kilogram and the total pressure is 1026.8 calculate the vapor pressure. So mixing ratio, we know the total pressure, we want to calculate vapor pressure. We try to express vapor pressure in terms of mixing ratio because that is the only quantity that we have. So basically the vapor pressure or the pressure exerted by any constituent in a mixture of gases is proportional to the number of moles of the constituent in the mixture. So here the mixture is basically of moisture and dry air. So the amount of vapor present is given by number of moles of vapor by total number of moles of the mixture. So NV by NV plus NV. E is equal to NV by NV plus NV into the total pressure. So number of moles we represented it in terms of mass. So if M present, mass of vapor present, then basically number of mass of vapor present by the molar weight of vapor, water vapor. So MV by MV by same thing for NV and NV we did. Then we multiply both the numerator and denominator by 1 by small md, mass of dry air, so that we can represent it in terms of mixing ratio. So after multiplying, we got it as W by MV by W by MV plus 1 by MV. Now we took 1 by MV common from both numerator and denominator, and we finally got W by W plus MV plus MV. So this is capital MV by capital MV. So capital MV, which is the molar weight of vapor, is given by 18.01 gram, and the molar weight of dry air is given as 28.9 gram. So basically, if we divide it, we will get the value 0.622, which is the same as RD by RM. So this ratio, RD by RM or MV by MV, is basically represented as epsilon. So epsilon is equal to 0. Substituting the value of M, we got E is equal to W by W plus E into P. So now we can calculate E from mixing ratio and the total pressure. So now if we substitute and calculate E will be, what is the value of W? 5.5 into 10 raised to minus 3 kilogram per kilo. We have to do the calculations in SI units. 5.5 into 10 raised to minus 3 plus 0.622 into the pressure. Pressure is 1026. Again we have to multiply into 10 raised to 2. Yeah, became so much messy, right? Into 10 raised to 2 will also come. So it is basically 5.5 into 10 raised to minus 3 by 5.5 into 10 raised to minus 3 plus 0.622. The whole multiplied by 1026.8 into 10 raised to 2. Because it is in hectopascal, we have to convert it into pascal. So can you calculate and tell me what will be the value of vapor pressure? Yeah, 900. What will be the unit? We calculated pressure. What is the unit of pressure? Yeah, the unit of pressure is pascal. So you calculated the value that you got is 900 pascal, which is equal to 9 hectare of the pascal. So the pressure exerted by the water vapor present in the air pascal, that is 9 hectopascal. So we calculated. So the equation of vapor pressure in terms of mixing ratio is E is equal to W by W plus epsilon into P, where P is the total pressure, W is the mixing ratio, and epsilon is the value 0.62. So that is the vapor pressure of the pressure exerted by water vapor in that mixture or in that air pass. Okay. Yeah. Okay, I think it's the same question. Same question. Okay. Now let's do another problem regarding the virtual temperature. So I hope you guys remember virtual temperature that we were discussing in the last class. So virtual temperature is basically the temperature that an vessel would have if it has the same density as that of a moisture vessel. So suppose there is a dry air parcel of temperature and density rho d. There is a moisture parcel at temperature T and density rho d. We want rho d to become equal to rho d. So density of dry air parcel to be equal to the density of moisture air parcel. So since the density of vapor is less than the density of dry air, we will have to reduce the density of dry air parcel. So in order to reduce the density, the way is to increase the temperature. So by increasing the temperature, at some point, the density of dry air and density of moisture will be equal. That temperature is basically known as a virtual temperature. Why did we introduce such a quantity? Because in case of the ideal gas equation for moisture, P alpha is equal to RT, or P is equal to rho RT. So in case of dry air, we learned PD is equal to rho RD into T. And in case of moisture, we learned E is equal to, or vapor pressure is equal to rho Rm into T, where rho and rho V. So Rm into T. So if you are considering an air parcel which is a mixture of both dry air and vapor pressure, which is E, we will have to define another equation of state where P is equal to rho R dash into T, where R dash will basically depend on the value of specific gas constant R dash will depend on the amount of water vapor present in the parcel. So as the amount of water vapor changes, the value of R also changes. So in order to avoid this inconvenience of calculating the value of R multiple times, what we did was that we changed the temperature from actual temperature T to the virtual temperature TV, so that we can retain the value of R to be RD, R dash to be RD. So in that case, we can write P is equal to rho M RD into TV. If we replace the temperature by virtual temperature in the ideal gas equation, we can retain the value of RD. We don't have to calculate R dash each time based on the amount of water vapor present in the parcel. So for this purpose, we introduce this temperature, virtual temperature. So the question is to calculate the virtual temperature TV if the actual temperature is 30 degrees Celsius, that has a mixing ratio of 20 gram per kilogram. So mixing ratio W is given as 20 gram per kilogram. The equation of virtual temperature in terms of R is basically mixing ratio. R is TV is equal to T into 1 into R, 0.61 into R. So I'll just show you how did we derive at this equation. So if you guys remember, the equation of virtual temperature that we learned was TV is equal to P by 1 minus E by P into 1 minus epsilon, where epsilon is equal to 0.622. This was the equation that we have learned of virtual temperature. Now, just now we learned that E is equal to W by W plus epsilon into P. That is vapor pressure in terms of mixing ratio. So E by P can be written as W by W plus E. If we substitute this in this equation, it will become PV is equal to P by 1 minus W by W plus epsilon 1 minus epsilon. It will turn out to be like this: W into 1 minus epsilon by W plus E. So basically it will become PV is equal to T into W plus epsilon by 1 epsilon into 1 plus W. If you expand this equation, it will become like this. If you expand this, W plus epsilon minus, it will become W plus epsilon minus W plus epsilon into W. This one, TV is equal to T by W plus epsilon minus W plus W into epsilon into W plus epsilon. This will become, so W and W will cancel out. From this, if we take epsilon out, it will be this W inside. So we have derived at the equation TV is equal to T into W plus epsilon by epsilon into 1 plus W, where W is the mixing ratio and epsilon is having the value 0.62. Now, further simplifying it, so the equation that we have now is TV, crystal temperature, is equal to T into W plus epsilon by epsilon into 1 minus W. This is 1 plus W. This is the equation that we have now. So this 1 by 1 plus W can be written as, if we divide 1 minus W by 1 minus W in both the numerator and denominator, it will become 1 minus W by 1 minus W square, A square minus A plus B into A minus B, A square minus B square. So it will turn out to be like that. So T into W plus epsilon into 1 minus W by epsilon into 1 minus W square. TV will become like this. So now if we are expanding the brackets, we will get T into W minus W square plus epsilon minus epsilon W by epsilon into 1 minus W square. So if you guys remember, the value of W is very small, like this much gram per kilogram. So it is like, suppose if it is 20 gram per kilogram, it's basically 20 into 10 raised to minus 3 kilogram per kilogram. So when it will become square, it will become a quantity which is having an order of magnitude of 10 raised to minus 6, which is very less. So we can neglect the terms which are having W square. Then it will become TV is equal to T into W plus epsilon minus epsilon W by epsilon, after neglecting the terms which are having W square. Then we have TW plus T epsilon minus T epsilon W to TV epsilon. This can be written as TV epsilon minus T epsilon is equal to TW into 1 minus epsilon. So if we take epsilon outside, TV minus T, difference between virtual temperature and actual temperature is equal to actual temperature into mixing ratio into 1 minus epsilon. For TV minus T can be written as TW into 1 minus epsilon by epsilon. It will become 1 minus epsilon by epsilon. We can calculate the value. We know the value of epsilon, which is 1 minus 0.622. 1 minus 0.622 divided by 0.622. It will give a value of approximately 0.61. So this will become TW into 0.61, which can be written as TV is equal to T plus TW into 0.61, which can be written as TV is equal to T into 1 plus 0.61. So this is the equation of virtual temperature in terms of actual temperature and the mixing ratio W. I hope the derivation is clear. So we started from the equation of virtual temperature that we know, which is basically TV is equal to T by 1 minus E by P into 1 minus epsilon. This is the equation that we had derived earlier. And just now we derived the equation for vapor pressure in terms of mixing ratio, which is E is equal to W by W plus epsilon into P. So from this, if we are finding E by P, it will come as W by W plus epsilon. Substituting the value of E by P in the equation of virtual temperature, we will get TV is equal to T by 1 minus W by W plus E into 1 minus epsilon. So multiplying W plus E to the numerator, TV becomes T into W plus epsilon by, and opening the brackets, that will become W plus epsilon minus W plus epsilon into W. Then it will finally reach the form TV is equal to T into W plus epsilon by epsilon into 1 plus W. Now the term 1 by 1 plus W, the term 1 by 1 plus W, this term 1 by 1 plus W can be written as 1 by W by 1 plus W into 1 minus W. We multiplied 1 minus W in both numerator and denominator. So it turned out to the form 1 minus W by 1 minus W square. We substituted it here and then expanded the bracket. And finally, we reached at this equation, which is TV is equal to T into 1 plus 0.61 to W. After neglecting the terms which is of second order W square terms, we neglected, and then finally we reached at this equation. TV is equal to T into 1 plus 0.61 to W. So this is the equation that we are going to use. So what all things have been given in the question? So we want to find the virtual temperature correction. Virtual temperature correction means TV minus T. How much is the difference between the virtual temperature and the actual temperature? That is TV minus T. So we want to calculate TV minus T for moisture at 30 degrees Celsius. So 30 degrees Celsius is the actual temperature, and the mixing ratio is 20 gram per kilogram. So T, the actual temperature of the parcel, is 30 degrees Celsius. Is equal to 30 plus 273. That much Kelvin. Basically 303 Kelvin. And the mixing ratio W is given as 20 gram per kilogram. Right? Just 20 into 10 raised to minus 3 kilogram per kilo. Now we want to calculate TV. TV is given as T into 1 plus 0.61 into W plus 303 into 1 plus 0.61 into 20 into 10 raised to minus 3. Which will be, can you calculate and tell me? How much it will be? Yeah, it will be 306 Kelvin. So this is the virtual temperature. They have asked, the question is to find the correction of virtual temperature. This is the difference between PV and T. That is 306 minus 303. This is 3 Kelvin. The difference between virtual temperature and actual temperature is 3 Kelvin. If you guys remember, I told you that since the density of vapor is less than the density of dry air, in order to attain the same density as that of the vapor, we will have to increase the temperature of dry air. So generally the value of virtual temperature will always be greater than the actual temperature. Just that how we found now. We have to raise the temperature of the parcel, raise the temperature of the dry air in order to have the same density as that of vapor. So in all cases the value of virtual temperature will be greater than that of the actual temperature. Like we got 306, the actual temperature was 303. The difference is around 3 Kelvin. 3 Kelvin is a virtual temperature correction. Okay. I hope it is clear. So we learned what is potential temperature. So potential temperature is basically the temperature that an air parcel would attain if it is adiabatically expanded or compressed to a standard pressure level, which is generally taken as 1000 MB or 1000 hectopascal. And another temperature that we learned was virtual temperature. So virtual temperature is the temperature would attain, air parcel would attain if it had the same density as that of the moisture air parcel. So that is virtual temperature. And then we learned two moisture parameters, which was first one was mixing ratio. Mixing ratio was basically is W is equal to mass of vapor by mass of dry air. Then we learned what was specific humidity Q, which was mv by mv plus mv, mass of water vapor to the total mass of air parcel. We also learned to express vapor pressure in terms of mixing ratio, W plus 1 plus W into P. And we also learned to express the virtual temperature in terms of mixing ratio, which was 1 plus 0.61 into W. Okay, I think it is clear till now. This much things we covered. So now let's move on to some other temperature. Before moving on to other temperatures, I wanted to introduce or just revise another quantity which you would have learned, which is basically the saturation mixing ratio or saturation vapor pressure. Just initially let's analyze the term saturation. Saturation is saturation vapor pressure. Consider that there is a container which is filled with water. Closed container which is having water, let it be at a temperature T. At this temperature T, some of the water molecules from the water surface try to evaporate and will form water vapor molecules above the water surface. And these water vapor molecules will exert a vapor pressure to the water surface, that is given by E. So the vapor pressure exerted by the evaporated water molecules with respect to the plane surface of water is vapor pressure E. So there will be a rate of evaporation. So how much water is getting evaporated. So along with evaporation, some of these water molecules collide with each other and some will come back to its original state. Thus it is condensed back to water form also after forming the molecules. So there will be a rate of evaporation, which is from the water molecules, how many molecules are escaping and then becoming vapor molecules in gaseous form. And after becoming vapor, some of these molecules collide with each other and may come back to its original state, which is liquid. So that condensation will also be there. So there will be rate of evaporation and there will be rate of condensation. So at the point when rate of evaporation of water molecules will become the rate of condensation. We will say the vapor or the air above the water surface is basically saturated, which means the amount of water vapor. So there is air above the water surface, right? Suppose it is an air parcel. So for each air parcel, there will be an amount of water that it can hold. If it exceeds the amount of water vapor that the parcel can hold, then condensation will start to begin, or both evaporation and condensation will become equal. So basically saturation means, or if we say that an air parcel is saturated, it means it has reached the level or reached the point at which it can hold the maximum amount of water vapor, which means the parcel is now holding the maximum amount of water vapor that it can hold. If we add more water vapor, it will start to condense and will start forming water droplets. So that is basically saturation. So when a parcel reaches saturation, the vapor pressure exerted by the water vapor molecules in the parcel is basically known as saturation vapor pressure. So this is basically represented with respect to a plane surface. So generally in case of water vapor, we represent saturation vapor pressure with respect to a plane surface of water, with respect to a plane surface of water. So the pressure that the water molecules are exerting in this water surface is basically vapor pressure. So saturation vapor pressure is when the rate of evaporation and rate of condensation becomes equal, or in simple terms, when the parcel is holding the maximum water vapor molecules that it can hold, the vapor pressure exerted by the water molecules at that particular point is known as the saturation vapor pressure. So this saturation vapor pressure is actually a function of temperature. So an air parcel will have a particular value of saturation vapor pressure at a particular temperature, and this is basically directly proportional. Higher the temperature, suppose we are increasing the temperature of a parcel. So as I told earlier, if we are increasing the temperature, the volume of the parcel also increases, like it expands. So if we are increasing the temperature of the parcel, the amount of water vapor that it can hold in that parcel will also increase. So the saturation vapor pressure also increases. So it will take more time for the parcel to be saturated. So suppose at a temperature of 20 degrees Celsius, the air parcel was able to hold around 20 water molecules. And when the temperature was increased to 30 degrees Celsius, the parcel expanded. It has more space now, so it can hold 30 water molecules. So if we want to say the parcel has reached saturation, the number of water molecules that the parcel might be holding should be 30 instead of 20. I'm just telling you example to get a better idea, to get clear with the concept. So this is what the saturation vapor pressure and temperature. So this is directly proportional. If we increase the temperature of the air parcel, more will be the amount of water vapor that it can hold, and more will be the saturation vapor pressure. So we have quantities like saturation vapor pressure, saturation mixing ratio. So saturation mixing ratio is same thing. When the parcel becomes saturated, what will be the amount of vapor present in the parcel? So it is mass of water vapor. S represents saturation by MT. Saturation mixing ratio is WS is equal to MBS by MT. And in terms of density, we can write WS is equal to, since the volume is the same, rho V S dash by rho D dash. Mass instead of mass, we can write in terms of density, rho V S dash by rho D dash. So rho, according to the ideal gas equation, P is equal to rho RT, or rho is equal to P by RT. So in case of water vapor, it will be E by R N into T by, in case of dry air, it will be P minus E, where P is the total pressure. So the pressure exerted by the dry air will be total pressure minus vapor pressure. So P minus E by RD into T. So if we cancel T and T, it will basically be E by P minus, it will be ES, sorry, since it is saturation, we are talking about the saturation. Same thing can be derived for unsaturated also. So ES by P minus ES into RD by R, which is again 0.62. So this will become ES by P minus ES into 0.622. So WS will become ES by P minus ES into 0.622. Since the value of ES is very much less compared to the total pressure P, P minus ES can be written as P. So basically WS will become ES by P into 0.6. This is the maximum ratio in terms of vapor pressure and the total pressure. Same thing can be written for unsaturated condition. So in that case, W will be E by P into 0.6. So maximum ratio in terms of vapor pressure. So I hope saturation, the concept of saturation is clear. So saturation vapor pressure is the vapor pressure that it exerts with respect to a plane surface of water when the parcel is saturated. So there are two ways to attain saturation. So as I told, when we increase the saturation vapor pressure is a function of the temperature of the parcel. So as I told, when we are increasing the temperature of the parcel, the saturation vapor pressure also increases. Whereas when we are decreasing the temperature, the saturation vapor pressure also decreases. So when we are decreasing the temperature, the air parcel becomes more compressed. So the amount of water vapor molecules that it can hold also reduces. So saturation vapor pressure also reduces. So this problem we already did, but I'll just use the space to explain one more parameter. We already did this problem. Yeah. So another moisture parameter is basically relative humidity. So we learned mixing ratio, specific humidity, saturation vapor pressure, and now relative humidity. So relative humidity is basically the ratio of actual mixing ratio to the saturation mixing ratio of the parcel into 100. It is generally expressed in percentage. So basically, it means how much is the amount of water molecules that the parcel is holding now and how much is its maximum limit. Suppose the water molecules is holding 20 water, suppose the air parcel is holding 20 water vapor molecules, and the maximum capacity of the air parcel is 30 water vapor molecules. Then it's basically 20 by 30 into 100. So how much it is actually holding to the maximum amount of water vapor that it can hold. That is basically relative humidity, W by Ws into 100. So generally for condensation to happen, the relative humidity should be 100%. The relative humidity is 100% in the sense that the actual saturation vapor pressure of the parcel is equal to its saturation vapor pressure. So which means the parcel has reached its maximum limit. It can hold this much of water vapor. It has reached that maximum limit. So that is relative humidity. So then we say that the parcel is 100. The relative humidity of the parcel is 100%. It is completely saturated. Okay. Then basically after when the relative humidity is 10%, then it starts condensing. Once it has reached the limit of the number of water molecules it can hold, then the process of condensation happens. So that's how clouds are formed. we need to attain specific level of relative humidity of 100%, or we need to attain the level of saturation for the cloud droplets, or for the water vapor molecules to condense and form the cloud droplets. So this is the condition of relative humidity to be 100%, and the vapor pressure, the mixing ratio, and saturation mixing ratio is important. Is important in case of cloud formation, cloud droplets and all. So yeah, so now let's learn some more temperatures. The first one, so there are two ways for an air parcel to become saturated. First one, so we have an air parcel, okay, and we have to make it saturated. So the first method is to add more water. First method is to add more water vapor, or the second method, without adding water vapor, by reducing the temperature of the parcel. That way also we can attain saturation. The parcel can attain saturation. So for a parcel to attain saturation, there are two methods. One is to add more water vapor and then reach its saturation level, or the second one is to reduce the temperature. When we reduce the temperature, the level of the amount of water molecules, the amount of water vapor molecules that the parcel can hold will also decrease. So it will become saturated easily. At a lower, if it is not temperature, if an air parcel is not saturated at a temperature of 20 degrees Celsius, maybe if we reduce the temperature to 15 degrees Celsius, it may become saturated. So two methods are there, either by adding more water vapor or by reducing the temperature. Okay. So dew point temperature is a temperature that a parcel would attain when suppose T is the initial temperature of the parcel. Suppose T is the initial temperature of the parcel and R is the mixing ratio. So we want to make this is the characteristics of an air parcel. So now we want to make this air parcel saturated. So for that, as I told, one method, so we should not add any more water vapor to the sample. So without adding more water vapor, the way to make a parcel saturated is to reduce the temperature. So we are reducing the temperature of the parcel, and when we attain a particular temperature which is known as TD, or the dew point temperature, the mixing ratio of the parcel will become saturation mixing ratio. R will become RS. So that temperature is known as dew point temperature. And the whole process has to happen isobarically. That is, the pressure should remain constant. So what it basically says that it is assumed that no water vapor is allowed to enter or leave the sample of air. We have an air parcel, no water vapor is allowed to enter the sample or leave the sample, but we have to make the parcel saturated. So the only way is to reduce the temperature of the parcel. So while reducing the temperature of a parcel, at one particular temperature, the parcel will become saturated. The mixing ratio will become saturation mixing ratio. That temperature is known as the dew point temperature of the parcel. Okay. And if we reduce the temperature further below the dew point temperature, then condensation starts to occur. As I told, when the parcel has reached saturation, if we again decrease the temperature, or if we again add more water molecules to the parcel, condensation starts to occur in the parcel, because more vapor is coming, more than it can hold, that much vapor is coming to the parcel. So what it will do, it will condense the amount of water vapor that is present in the parcel in order to accommodate more number of water vapor molecules. So dew point temperature it is assumed that no water vapor is allowed to enter or leave the sample of air, so that the mixing ratio of the parcel remains constant. So no water vapor enters or leaves means the mixing ratio will be constant. And now the sample of moisture is cooled isobarically. We are cooling the parcel, that is, we are reducing the temperature of the parcel isobaric pressure and is eventually reached and the temperature is eventually reached at which it becomes saturated. And while we are reducing the temperature, the amount of water vapor molecules that the parcel can hold also reduces, and at one particular temperature it will become saturated. So that temperature is known as the dew point temperature of the parcel, or simply the dew point. So basically when T becomes TD, the temperature of the parcel becomes the dew point temperature. Then R is equal to RS and relative humidity is equal to 100%. Okay, so that is dew point temperature. The process is happening isobarically. So no water vapor is allowed to enter or leave the system. So the mixing ratio of the parcel remains constant and we are cooling the parcel isobarically, and the temperature is eventually reached at which the parcel becomes saturated. So this particular temperature is known as the dew point temperature, or simply the dew point. And if we reduce the temperature of the parcel again further below the dew point, then condensation starts to occur in the sample of air. Okay, so that is dew point temperature. Now, so this in this method we are saturating the air parcel without adding more water vapor, just by decreasing the temperature. Now another way to saturate an air parcel is to add more water vapor. So the next temperature, which is the wet bulb temperature, uses the second method, which is adding more water vapor. So what does wet bulb temperature mean? So we have a sample of air and we are constantly adding more water vapor to the sample by evaporation of liquid water. So we are adding more water vapor to the sample. In that case, the mixing ratio is not constant because we are adding more water vapor. So the mixing ratio is increasing. So in this case, R is increasing. We are adding more water vapor. So R is increasing. And at one particular point, R will become equal to RS. So as we are adding more water vapor to the sample of air, the latent heat for the change of liquid water into water vapor is supplied by the sample itself. So as a result, the air sample may be cooled to which it is saturated. This is known as a wet bulb temperature. So basically, so how we will temperature. So generally temperatures are measured using an instrument called as thermometer. So it will basically have a mercury bulb at the bottom, and then the measurement scale will be there. So based on the temperature, the mercury present in this bulb will expand, and the level up to which the mercury has expanded gives the temperature at that particular time. So this thermometer is basically known as dry bulb thermometer, or the temperature is known as dry air temperature, which is the temperature that all of we are familiar with, the actual temperature that we talk about. That is basically given by the dry bulb thermometer, or the temperature is dry bulb temperature. Now what is wet bulb temperature? So in case of wet bulb temperature, what we do is we have a wet moist cloth which is covered on the mercury bulb. So on top of the mercury bulb, we will wrap a wet or moist cloth. So it has a sufficient amount of water in the cloth. So what happens is that when air comes into contact with the mercury bulb, the air will be gently unsaturated, or the water vapor content in the air will be less. So what happens is that from the moist cloth, water molecules will start to evaporate and will keep on adding to the air parcel. So this is basically wet or water molecules are present in the cloth. So when air comes into contact, water molecules will evaporate and then will fill the air parcel around it, or the water droplets will evaporate and will add to the air parcel that is in contact with the parcel. So basically water vapor molecules are being supplied to the parcel. So in order for this evaporation to happen, some heat should be absorbed. So this is which is basically known as the latent heat of evaporation. If evaporation should happen, some amount of heat should be absorbed. So the amount of heat that is required for this conversion is absorbed from the air parcel that is in touch with the thermometer. So basically the temperature of the parcel will reduce. because it is being used for the process of evaporation. So water vapor molecules is being added to the system, and finally it will reach a temperature when R will become Rs. R will be keeping on increasing because of the addition of water vapor molecules, and at some particular temperature R will become Rs. That temperature is known as wet bulb temperature. So that is wet bulb temperature. So in case of wet bulb, we are adding more vapor to the sample of air. So wet bulb temperature is basically measured using wet bulb thermometer, which has a wet or moist cloth wrapped to the mercury bulb, which is in the bottom of the thermometer. So in this case, the mixing ratio of the sample is increased. So the latent heat of change of liquid water into the water vapor is supplied by the sample of air itself. As a result, the sample may be cooled to which it is saturated. So the temperature of the parcel will also be decreasing, and there will be addition of more water vapor. So at some particular point, the parcel will become saturated. That temperature is known as the wet bulb temperature. That is wet bulb temperature. Now another temperature is there, which is known as the equivalent temperature. So the dew point, I think you guys got dew point temperature, wet bulb temperature. Now the third one is equivalent temperature. So equivalent temperature is another isobaric process takes place for moisture if the water vapor in the sample condenses at constant pressure. In this case, the latent heat released. So this dew point temperature will always be less than the actual temperature, because we are cooling the past. The actual temperature is T. The actual temperature is T. Dew point temperature will be less than the actual temperature because we are cooling the air parcel so that saturation is attained. By cooling, we will reach a particular temperature when saturation occurs. So that temperature is known as dew point temperature. So cooling is happening. So TD will be less than T. And wet bulb temperature also will be less than the actual temperature because of this, because of the process of evaporation, that is the evaporation that is happening from the moist cloth to the air. So for the process of evaporation to take place, the latent heat of evaporation or the heat required is supplied by the air parcel itself. So basically the air parcel cools. So at particular temperature it will become saturated, and that temperature is wet bulb temperature. So TW will also be less than T. Now there is another temperature which is equivalent temperature, that will be TE. So in this case what happens is that suppose the water parcel is saturated, and once it is saturated, condensation starts to occur in the parcel. Okay, suppose consider that all the water vapor present in the parcel has been condensed and have formed water droplets. Water vapor molecules was present in the parcel has undergone condensation and has turned into water droplets. So in that case, the temperature reached is known as equivalent temperature. In this case, what happens is that here the process that is happening is latent heat of condensation. So latent heat of condensation is the heat that is being released, not absorbed. In case of evaporation, since the change of state is from water to vapor, the amount of heat is being absorbed by the system. And in case of condensation, the heat will be released. So since condensation is occurring in case of equivalent temperature, the temperature of the parcel will increase. So the parcel will be warmer than the actual temperature. So TE will be greater than T. So the temperature that the parcel will reach when all the water vapor in the sample is condensed is known as equivalent temperature. Okay, equivalent temperature is what? We have an air parcel which is saturated, and as I said, when the parcel is saturated, condensation starts to begin in the parcel. Consider that how much water vapor is present in the parcel has undergone condensation and has formed water droplets. So in this case, since the process that is happening is condensation and the change of water vapor to water droplets, there will be a release of heat, which is basically the latent heat of condensation. So this latent heat of condensation is used to warm the sample of air. So basically the temperature the parcel will reach when all the water vapor in the sample is condensed is called the equivalent temperature. So equivalent temperature will be greater than the actual temperature T, whereas wet bulb and dew point temperature will be less than the actual temperature T. I hope it is clear, all these temperatures. All these are new terms. Just get an idea or be familiar with the terms. What are these different types of temperatures? So I think till now we have learned 5 different temperatures: virtual temperature, potential temperature, dew point temperature, wet bulb temperature, and equivalent temperature. So these are temperatures that we use when we are dealing with moisture for different research purposes, different calculations. So now let's talk about a level. So lifting condensation level. So lifting condensation level is basically a particular height in the atmosphere or a level in the atmosphere to which an unsaturated air parcel has to be lifted adiabatically before it becomes saturated with respect to a plane surface of pure water. So as I said, if we want to make an air parcel saturated, two methods is one to add water vapor or to reduce the temperature. So in the atmosphere, if we have to reduce the temperature of a parcel, the method is to lift the air parcel. Suppose we have an air parcel here. If we want to reduce the temperature of the parcel, lift it vertically in the atmosphere, because as we go up in the atmosphere, the temperature decreases. If you remember, we learned the vertical structure of atmosphere, in which in the troposphere is having a decrease of temperature with respect to height. The lapse rate is negative in the troposphere. As we go up in the atmosphere, the temperature is decreasing. So if we want to reduce the temperature of an air parcel, we can simply lift the air parcel in the atmosphere. So when we are lifting an air parcel in the atmosphere, the temperature will decrease, and at one particular point it will become, at a particular height, the parcel will become saturated. So that particular height is known as the lifting condensation level. So in order to reduce the temperature of an air parcel and eventually reach the saturation, we are lifting an air parcel unsaturated, but it has moisture content in the parcel. So we are lifting an unsaturated moisture air parcel along the atmosphere adiabatically. We are not adding, no heat is allowed to enter or leave the system. So as I told, all atmospheric motions are considered to be adiabatic. So basically it is lifted adiabatically before it becomes saturated to a plane surface of water. So that particular level is known as a lifting condensation level. So during lifting, mixing ratio is constant. The potential temperature is also constant. Since the process is adiabatic, as I told, the potential temperature is also constant. So what is happening here is the saturation mixing ratio is reducing. So as the temperature is decreasing, saturation mixing ratio is also reducing. And at one particular temperature, which is when T becomes TD, so at this level, the actual temperature and the dew point temperature of the parcel is equal at the lifting condensation level. So at the lifting condensation level, the actual temperature becomes the dew point temperature, and the parcel has finally attained saturation. That level or that height in the atmosphere is known as lifting condensation level. So as we are vertically lifting the air parcel, the temperature of the parcel is reducing. The mixing ratio and potential temperature are remaining constant. Saturation mixing ratio is reducing. Actual temperature is also reducing. And once it reaches the lifting condensation level, R will become RS, T will become dew point temperature, and that level is basically known as the lifting condensation level. I hope it is clear. So, and then it's just latent heat. You are already familiar with the term. So basically, when we are supplying heat to a particular system under certain conditions, instead of producing a change in temperature, the system may undergo a change in phase. So in this case, water energy that we are supplying, so basically Q is equal to U plus W. No work will be done. Water energy we are supplying is used to increase the internal energy of the system. And again, internal energy in the sense, it has both kinetic and potential energy, microscopic kinetic and potential energy. If the temperature is constant, that means kinetic energy is not changing, and the only change that is happening is to the potential energy. So potential energy, microscopic potential energy is basically the intermolecular force of attraction between the molecules. So the microscopic potential energy is increasing, or the intermolecular force of attraction is increasing or decreasing, whatever is happening. So in that case, what happens is that if the intermolecular force, based on the what change is happening to the intermolecular force of attraction, the system will be undergoing a change of phase. either from vapor to water, vapor to liquid, or liquid to solid, or solid to liquid, whatever it is. So generally, if we are supplying heat to ice at a temperature of 0 degrees Celsius and at a pressure of 1 atmosphere, the temperature remains constant until all of the ice has melted, which is basically the melting point of water. So we have reached the melting point of water, which is 0 degrees Celsius, and we are supplying some heat to the water. Then instead of increasing the temperature of the water, what happens is that the water will start to solidify. And when we are supplying heat to ice basically, which is at a pressure of 1 atmosphere and temperature of 0 degrees Celsius, the ice will start to melt and the temperature will remain constant until all ice has melted. So based on the change of phase that is occurring, different types of latent heat is there. Latent heat of melting, latent heat of vaporization, latent heat of condensation, etc. So generally the change of phase if the change of phase is from liquid to vapor or vapor to liquid, either way it can happen. So if it is from liquid to vapor, it is latent heat of condensation, and if it is from vapor to liquid, it is latent heat of condensation. The magnitude of these two values will be same, just the sign will differ. That is, if it is the liquid is changing to vapor, basically there will be an absorption of latent heat of vaporization. And if the opposite it is happening, that is if the phase is changing from vapor to liquid, then there will be release of energy, which is basically latent heat of condensation. So in case of water vapor, we have constant values for all these latent heats like condensation. So latent heat of vaporization and latent heat of condensation will be equal. Magnitude will be equal. So in one case there will be release and in one case there will be absorption. And in case of ice and ice to water conversion, both solidification and melting, both cases latent heat of melting and latent heat of freezing will be equal, just that change of based on what phase change is occurring, the sign of the value will change. So that is all about latent heat. Okay. Now, so if you guys remember, we talked about dry adiabatic lapse rate in the last class, which is basically dt by how the, if suppose an air parcel, we are lifting an air parcel in the atmosphere, how the temperature of the parcel is changing. So dt by dz will change, rate of change in temperature with respect to the height. We got a value of 9.8 degrees Celsius per kilometer. If you remember, it was G by Cp. We derived the equation and then we calculated the value of 9.8 degrees Celsius per kilometer. So this is basically known as dry adiabatic lapse rate. In this case, we consider that the air parcel is unsaturated. So there is some amount of water vapor in the parcel, but it is not saturated. It is an unsaturated moist air parcel. So moist air parcel in the sense it has some amount of vapor in it. Dry air parcel in the sense it doesn't have any water vapor content in the parcel. So generally for an unsaturated moist air, which the temperature decrease as it ascends in the atmosphere is given by the dry adiabatic lapse rate, which is having a value of minus indicates decrease with respect to height, minus 9.8 degrees Celsius per kilometer. This is G by Cp. We calculated it in the last class. So suppose consider instead of unsaturated air parcel, we are considering a saturated air parcel. In that case, the lapse rate is called saturated adiabatic lapse rate, or SALR. dt by dz. So gamma T is dry adiabatic lapse rate. In case of an unsaturated air parcel, whereas gamma S, or saturated adiabatic lapse rate, is in case of a saturated air parcel. So saturated, okay, this is about process. Saturated adiabatic lapse rate, in contrast, dry adiabatic lapse rate. So dry adiabatic lapse rate is a constant value. We calculated the value which we obtained it to be. DLR we calculated, it was G by Cp. It was minus 9.8 degrees Celsius per kilometer. We calculated this value in the last class. So this is a constant, dry adiabatic gas rate. In case of an unsaturated air parcel, the rate at which the temperature decreases with respect to height is a constant, such as 9.8 degrees Celsius per kilometer. And in case of a saturated air parcel, the saturated adiabatic gas rate is not a constant. This is not a constant value in case of saturated. The value of saturated adiabatic gas rate, gamma S or gamma S, we can notate, like we can have the notation of the, like this one also, this one, both are gamma. So the value of saturated adiabatic gas rate is not a constant, but it varies with pressure and temperature. Based on the pressure and temperature of the parcel or the atmosphere, the value of saturated adiabatic gas rate changes. And because the water vapor condenses when a saturated air parcel rises. So in case of a saturated air parcel, if we are rising so an air parcel is saturated, suppose at this level, we are trying to rise the air parcel again. So if we are again rising the air parcel, particularly in the atmosphere, its temperature decreases. So as I told, at the saturation, temperature is equal to dew point temperature. This dew point, it has reached the dew point. Now if we are reducing the temperature further beyond the dew point, condensation will start to occur. So if we are rising a saturated air parcel further in the atmosphere, the condensation starts to occur in the parcel. So as condensation starts to occur, the water vapor present in the atmosphere will condense and form water droplets. And in this conversion, latent heat of condensation will be released. So even though when the parcel is moving up in the atmosphere, the temperature is reducing, because the latent heat of condensation is being released, there is some addition of Q. Some amount of heat is supplied to the system. So this temperature decrease won't be that much. It will be compensated somehow by the latent heat of condensation, the latent heat that is released. So generally the saturated adiabatic gas rate, or the rate at which the temperature of a saturated air parcel will decrease, will be less than that of a dry air parcel. So in case of a dry air parcel, and we are considering the rate at which the temperature is decreasing, it will be greater. That a saturated air parcel, if it is traveling a kilometer, vertically a kilometer of 1 kilometer, and the temperature is reducing by 1 degree Celsius, minus 1 degree Celsius. Initially the temperature was 21 degrees Celsius, and after vertically moving up in the atmosphere, its temperature reduced to 20 degrees Celsius in case of a dry air parcel. But in case of a moist air parcel, if the same moist air parcel is moving up in the atmosphere, and if the initial temperature was 21 degrees Celsius, after traveling 1 kilometer, the temperature would have reduced to not 1, maybe 0.8, 0.7, something like that. So it won't be 20 degrees Celsius, but maybe it will become 20.9, 20.8, 20.7, something like this. It will be less than the dry adiabatic gas rate. Saturated adiabatic gas rate will be less than the dry adiabatic gas rate, because when we are lifting a saturated air parcel further up in the atmosphere, condensation starts to occur, and as a result of condensation, latent heat of condensation will be released, which will be added to the parcel. So even though it is moving up in the atmosphere, its temperature is decreasing, there is some additional supply of heat which compensates the decrease in temperature. So the rate of decrease of temperature will be less compared to that of a dry air parcel. So that is saturated adiabatic gas rate. Now let's see what is a saturated adiabatic process. So as we just now told, when an air parcel is rising in the atmosphere, the temperature decreases at altitude at dry adiabatic gas rate. So initially we have an unsaturated air parcel. So initially we have an unsaturated air parcel, The parcel is raised in the atmosphere. Temperature decreases. At some level, Z is equal to LCL, it will become saturated. So we are rising the parcel, and at some point the parcel became saturated. So once the parcel became saturated, further lifting, if we further lift the parcel, condensation will start to occur, which releases latent heat. Consequently, the rate of decrease in temperature of the rising parcel will also be reduced. So dT by dZ will also reduce. And consider that all the condensation products. So condensation means water vapor molecules are getting converted into droplets. Suppose whatever condensation products, let it be water droplets or let it be ice particles, whatever is produced remain in the rising air parcel, that it is not precipitating. So there is air parcel, cloud droplets or water droplets are formed in the parcel, but it is not raining out. Condensation, whatever is produced, is staying in the parcel itself. So the process may still consider to be adiabatic. It is still adiabatic and it is reversible. Since whatever is produced is staying inside the parcel only, it has not left the parcel. So in that case, we say that the process is still adiabatic and reversible. Even though there is a release of latent heat, heat is being released, it is um, not leaving the system. Whatever heat is being produced due to latent heat of condensation is used to warm the parcel itself. It is not going out of the system. So in that case, the process is still said to be adiabatic, saturated adiabatic process. Now consider that after the condensation products are formed, maybe it will fall down as rain or snow or whatever it is based on the condensation products that is formed. So once the products has fallen out of the air parcel or fall out of the system, now the process becomes irreversible and not strictly adiabatic. So that once it rains out or once it precipitates out of the system, then the process is said to be pseudo-adiabatic, which means it is not adiabatic anymore. The process is not reversible. And the condensation products, when it is falling out, it will carry some heat also. So there is a removal of heat from the system. So now the process doesn't remain to be adiabatic anymore. That process is said to be pseudo-adiabatic. So what we did, we have an unsaturated air parcel. We were rising it up in the atmosphere. As we were rising, the temperature was decreasing. The saturation mixing ratio was decreasing. And at some particular point, the parcel became saturated. So after it became saturated, when we rise the parcel further in the atmosphere, or if we reduce the temperature of the parcel further, then what happens? Condensation starts to occur in the parcel. So condensation means water vapor is being converted to water droplets. So whatever water droplets are found, consider that it is remaining, and whatever latent heat of condensation is produced is used up in the system itself. It is just used to increase the temperature of the parcel. It is not leaving the system. So in that case, we say that the process is still adiabatic, and that process is known as saturated adiabatic process. Now consider that whatever water droplets or ice particles that are formed, or the condensation products that form, immediately fall out of the air parcel. So water condensation products that have been formed in the parcel is falling out of the system. In that case, the process is no longer reversible. It is an irreversible process, and it is not adiabatic anymore. So some matter is getting released by the system, and there is also removal of heat from the system. So condensation products also carry some heat. So now the air parcel is said to be pseudo-adiabatic. It is undergoing a pseudo-adiabatic process. So that is saturated and pseudo-adiabatic process. I think I will end it today because if I go further, you will get confused again. We will talk about these things in the next live practice session. I think I have bombarded you with a lot of new terms and a lot of new things. I think we'll end it for today. I'll just revise whatever we learned. Yeah. I have a question. So I think we'll just conclude and then we'll start the class for today. So the things that we learned today first was the potential temperature. The potential temperature theta of an air parcel was defined to be the temperature that the parcel would have if it was expanded or compressed adiabatically from its existing pressure and temperature to a standard pressure P0. So theta is defined to be T is the actual temperature of the parcel into P0 by P, where P0 is the surface pressure and P is the pressure at that level, whole raised to R by C. And this is a conserved quantity. When we are considering air parcel motion in the atmosphere, potential temperature is said to be a constant, or it is a conserved quantity. So that is potential temperature. And we just learned how it is derived. Yeah, then we did some problems. Then we learned two new terms, which was mixing ratio and specific humidity, which are basically moisture parameters. These terms are used to express the amount of water vapor that is present in an air parcel. So mixing ratio is given as mass of vapor to mass of dry air, MV by MT. It is represented in gram per kilogram. This much of vapor, this much gram of vapor in this much of kilogram of dry air. That's how it is represented. The value is high in tropics as we are going from the equatorial region high to more latitudes or to high values of latitudes. The the availability of moisture decreases because of the decrease in temperature, and the mixing ratio also decreases. So the highest value of mixing ratio is found in the tropics. And then the second one we learned was specific humidity, which is given by mass of water vapor to the total mass of air, mv by mv plus mv, which is again represented in gram per kilogram. Then we just learned the equation of vapor pressure in terms of mixing ratio, which is E is equal to W by W plus epsilon into. Then we learned the term called saturation vapor pressure, which is basically the vapor pressure that an air vapor molecules will exert when the parcel is saturated, when it has reached the maximum capacity, maximum holding capacity. So this is basically a function of temperature. As the temperature increases, the vapor pressure also increases, and as the temperature decreases, the vapor pressure also decreases. And we also learned relative humidity, which is basically the actual mixing ratio of the parcel to the maximum it can hold. So W by Ws into 100, because it is expressed in percentage, we find the ratio and it's multiplied by 100. So relative humidity is 100% in the sense the parcel is now holding the maximum amount of water molecules that it can hold. So basically the mixing ratio of the parcel will be equal to the saturation mixing ratio. So that is relative humidity. Yeah, that's what temperature we already learned in the last class. And then we learned three new temperatures: dew point, wet bulb, and equivalent. As I said, if we want to saturate an air parcel, there are two methods. One is to reduce its temperature, and second one is to add more water vapor. So in case of dew point temperature, we are reducing the temperature of the parcel and then reaching saturation. So that temperature is basically known as dew point temperature. And in case of wet bulb temperature, more water vapor is being added to the parcel and then we are reaching saturation. In both cases, the temperatures will be less than the actual temperature. And the third one we learned was equivalent temperature. Equivalent temperature in the sense that the all the water vapor which was present in the parcel is getting condensed, and the temperature of the getting all the water vapor which is present in the system is turning to water molecules. So at that time, latent heat of condensation will be released, so the temperature of the parcel increases. So in that case, the temperature that we get, which is equivalent temperature, will be greater than the actual temperature. So that is equivalent temperature. These are the three different temperatures that we learned. We learned about dry bulb thermometer and wet bulb thermometer also. Wet bulb temperature is basically measured using wet bulb thermometer, which is basically a thermometer which with a moist cloth which is wrapped around the mercury bulb in the bottom of the thermometer. So that is wet bulb thermometer. So water vapor is being added to the parcel, is being evaporated from this moist cloth. Then we learned a level or the height at which the saturation occurs, which is the lifting condensation level. At lifting condensation level, the temperature of the parcel will be equal to its dew point. Relative humidity will be 100%. Mixing ratio will be equal to the saturation mixing ratio. And the actual mixing ratio of the parcel and the potential temperature remains constant. And we learned latent heat also. And lapse rate, saturated adiabatic lapse rate we learned. So saturated adiabatic lapse rate is in contrast to dry adiabatic lapse rate, it is not a constant. The value depends upon the pressure and temperature, and generally, because the in case of a saturated air parcel, because the condensation, because the occurring of condensation and the release of latent heat of condensation, the value or the rate at which the temperature decreases as we move up in the atmosphere is less compared to that of an unsaturated air parcel or dry moist air parcel. So less than dry adiabatic lab state. So basically, saturated adiabatic lab state will be less than the saturated adiabatic lab state will be less than the dry adiabatic lab state. And we learned two processes: saturated adiabatic process and zero adiabatic process. Saturated adiabatic process when the air parcel when a saturated air parcel starts to condensation occurs in a saturated air parcel, but the condensation products are not leaving the system, and whatever heat is being released due to the latent heat of condensation is staying in the system itself. The heat is used to increase the temperature of the air parcel itself. So in that case, this process is said to be saturated adiabatic, and when the condensation products that are formed during condensation is falling out of the system or is falling out of the air parcel, there is removal of heat also, as the condensation products carry some heat along with it. So in this case, now the process is not and does not adiabatic. So that processes are called pseudo adiabatic process. So I think that is more than enough for today. We will end the session here. Yeah, yeah. Uh, you can, yeah, you can. Send me a mail. I can give you, I think my mail ID you can get from this meeting, right? And you, yeah, so you just send me a mail. I can share the contact information. Okay.